Hi friends, welcome back to the course. Today we will be doing a problem from the textbook Mechanics of Materials written by Timoshenko. This is a relatively simple problem, but I believe that by solving this problem you will get an insight into the system, the cylinder piston arrangement, which we will see a lot of times as a mechanical engineer. So we will understand a few basic considerations that goes into designing of such an engine. We won't get into the details, but on a preliminary level, what are the calculations that they will be doing? So here we have a piston as shown over here. It is connected to the crank using a connecting rod. So combustion of the gases will be occurring somewhere here. So this high pressure gas will push the piston from this side. So the force with which this gas will act against the piston is given by capital P. So the question is, let's say if sigma allowable is the compressive stress, it is the allowable compressive stress in the connecting rod, then what is the maximum force with which this gas can push against the piston? I hope the question is clear. And there are few assumptions. There is no friction. So drawing the free body diagram and everything becomes a lot more easier. As I say all the time, there is only one single tool that comes to our rescue all the time when we solve problems of this kind, that is free body diagram. So let's say first I'm starting the discussion by drawing the free body diagram of piston. So here you have the piston and I have shown the different forces. So here is the force that comes from the gas and here is the weight of the piston, and it will get cancelled by the normal reaction provided by the cylinder onto the piston. And this particular force, this is the reaction force that is coming from the connecting rod. So this is the force that the connecting rod exerts on the piston. Make sense? Now if I go ahead and draw the free body diagram of my connecting rod, since it is a two force member, I'm assuming that it is a two force member, there is no friction at the joints and there are no external forces acting on the connecting rod, then it's a two force member. For a two force member to be in equilibrium, then the forces should act in opposite direction and they should be the same in magnitude. So I can say if this is the force and the direction in which a connecting rod is applying a force on the piston, so the piston will apply an equal and opposite force by virtue of Newton's third law. So I can completely describe the external force that is acting on the connecting rod at this point. For the connecting rod to be in equilibrium, there should be an equal and opposite force that is acting like this. So in a nutshell, the force acting on the connecting rod is FCR. Now how I can compute FCR in terms of other parameters which are known to me? Capital P is known to me. Because actually I need to compute what is the maximum P allowable for an allowable compressive stress of sigma C in the connecting rod. So the next step is writing the equilibrium equations for the piston. I can state that everything is at rest. See, we are not getting into the dynamics of this whole motion. We are saying freezing at a point or freezing a particular time instant. We are solving this. For explaining it further, it's like this whole system is moving, but for the time being I'm thinking that I'm worried only about the static application of forces. I'm thinking that there is someone pushing at the piston with a force capital P and someone is resisting the motion of the crank with a resisting moment capital M. So everything is in static. So that's why for the piston I am taking my equations of motion or equations of equilibrium like this: sigma fx equal to 0 and sigma fy equal to 0. Simple. Sigma fy equal to 0 simply means the normal reaction should be equal to the weight of the piston. Now when I sum the forces along the x direction, then I get something like this: FCR cos alpha equal to P, which helps me to write this particular expression. Well and good. Now I know what is the force acting on the connecting rod, then I can go ahead and write the formula for the axial compressive stress that is acting on the connecting rod, which is simply the force times the, see, there is no FCR in this formula. This FCR corresponds to the figure. This is the final expression for which tells you what is the stress, what is the compressive stress that is acting on the connecting rod. So now something interesting turns up. There is a cos alpha term. So you need to tell me what is the maximum P allowable. For that, you should be knowing what is the maximum compressive stress that will be coming to the, or that will be experienced by the connecting rod. See, 4P is a constant, D square is a constant, everything is a constant other than cos alpha. Cos alpha is changing as our system is rotating. See, as the crank rotates or as the piston moves to and fro, this particular value of alpha is changing. So I am interested in this value. I am interested the maximum value of the compressive stress, which in turn means I'm looking for the minimum value of cos alpha, because when cos alpha assumes a minimum value, that is the particular instant when I will see, or when I will see a maximum compressive stress in my connecting rod. Make sense? Cool. Now from this geometry, let's assume that this angle is beta and this angle is alpha, that we have assumed in the earlier figure also. What I can say from this particular figure is that this particular vertical line that I have drawn can be thought of as the part of these two triangles. It can be thought of as an edge of this triangle as well as this triangle. From this triangle I can equate this length to be L sine alpha, and from this triangle I can equate that length to be equal to R sine beta, where R is the radius of the crank. Capital R is the radius of the crank. It is given here. So now from this expression I can go ahead and write cos alpha like this, and simple substitution will get me somewhere here. Now I was looking at what was the minimum value of cos alpha. Now by looking at this expression, I can say that for cos alpha to be minimum, this value should be maximum, because we have a minus symbol over here, or we are subtracting this whole quantity from 1. So for cos alpha to be minimum, this should be maximum. See, R square is a constant, L square is a constant. Beta is something which changes, but doesn't matter what is the variation in beta, the maximum value of sine square beta is always going to be 1. That will correspond to the minimum value of cos alpha. So we are seeking for a minimum value of cos alpha, so maximum value of sine square beta will be equal to 1, which in turn tells me that the minimum value of cos alpha is root of 1 minus R square by L square. This will correspond to a case of beta equal to 90 degree, which means that when the crank is at this location, you can see the connecting rod will be somewhere here, and see, actually at this point only you are seeing a maximum stress in the connecting rod. Make sense? Now it's simply plug and chug. Now you know what is the maximum compressive stress that you are expecting in your connecting rod. It can be written like this. So this is the maximum compressive stress. So we have an allowable compressive stress in the connecting rod. So equate these two. Now from this we can express the maximum force which the combustion gas or the high pressure gas after combustion can exert on the piston. In terms of the allowable compressive stress that comes from the material properties of your connecting rod, d square is the dia of your connecting rod, and L is the length of the connecting rod, capital L, and capital R denotes the radius of the crank. So in terms of all the known parameters, we can express the maximum force that is allowed, P allowable. So this is the answer. Thanks for watching.